the first reaction in this series is statistical distribution. We talk a lot about different like Poisson distribution, use normal distributions, chi-square, and different other terminology, but we actually sometimes don't have any idea what it is. So I will try to explain what it is. So this is my acknowledgement. I would like to begin by acknowledgement that the land on which we gather today is unceded territory of the Coast Salish people. And to make it personal, I wanted to say that this Sunday, Jewish people will observe Yom Kippur. And actually Yom Kippur is the day when you try to reconcile with God. So basically you're looking on yourself, it's a day of reflection of you, of people around you. It's day of forgiveness. And in addition to it, what happens this year on Yom Kippur, that unfortunately our parliament was cheering for the Nazi hero on public, and it was very hard day for me. And I think why it was so hard the date for me, I want to hope that this mistake was like by mistake and there is nothing behind it. And I also hope that all apologies that we heard over this time was sincere apologies. But I think it showed me how ignorant we are in our society for the history and experience of other people around us. We say something, we do something, and we don't know how it's affecting people around us. And I think for me, the main point of reconciliation, it's respect the history of people around me and respect the experience. Because I think if you respect experience of other people, you really trying to reconcile. Thank you. So now for the lecture, the objective of the lecture is to understand the foundational concept of statistical distribution, including different types of variables, different terminology of distributions, and also to show you how those distributions are different, what distributions they are, and to try help you to understand the characteristics and properties of those distributions. What I think this lecture, compared to all my other lectures, will be more statistical, because you cannot talk about the distributions without talking and including some formulas inside your presentation. So to talk about the distribution, we need to understand what is sample or outcome space. We usually talk about samples. So, we selected the random sample. Our sample was not randomly selected, it's self-selected sample. But we're talking basically of people, subjects, or events we randomly selecting. But sample or outcome space is actually collection of all possible outcomes of our random study. For example, we try to measure the height of the children in population in BC. We pick up some children will be our sample, but our sample space will be actually the measure of their height. So basically, generally in statistics, we're talking mostly of discrete variables, the variables that we can count, and continuous variables that the all possible values between selected 2 points. So here is some more example of type of variables. Discrete variable, it finito countable number of values typically arise from the counting process. So basically anything we can count, we can say that this is discrete variable. So it can be number of cars in parking lot, number days of January, different car brands. So we can look on it as categorical variable, because usually in our analysis we say, oh, this variable is category. And and it can be like categories that we can count and there is meaning for our count, or just random numbers that we assign to our category. So, and our typical like variables that we use as yes, no, it's actually considered discrete variable. What are continuous variables? This is infinite number of values that contains in some kind of interval. So it can be time, weight. So basically, it can be every hour, how many hours above zero we spent or something else. So it's not all possible numbers in our real world, in our number space, but it's actually selected infinite number of points within the interval or above selected point. So there is very complicated terminology of it, because I Googled a lot of things, and very respectable websites actually use the terminology not always correctly. They sometimes change it, but the terminology actually very simple. When we're talking about probability density function, we usually talk about continuous random variables. So variables in our measures in our random space. When we're talking about discrete random variables, we're talking about probability mask function. It's not the same, and I show you later why. And when we talk probability distribution function, we usually mean either discrete function or continuous function. To go more deeply in the terminology, so if x is discrete random variable we can count, the probability mask function of x equals some number of x will be p at x, basically probability of x. And we use p of x to notate the probability mass function. When we're talking about probability discrete function, it's analog of a mass function, but for continuous variables. If we consider an x to be continuous random variable, the value of probability density function x being some kind of number of x will be f at x. So it's very important when you write something to use those notation correctly, because it can be very misleading. And also continuous function in specific point x, it's not exactly the same as probability for this point for x. Actually, probability of specific point for continuous distribution always will be 0. More about terminology. Additional terminology we usually use is cumulative distribution function, and usually it's calculates as area under the curve. And for statistical distribution, we usually look on the numbers from some point x to the left. And for continuous function, area under the curve, it's actually our probability. For discrete variables, because if you look on it as a frequency plot with bars, with the spaces between bars, yeah, we only can calculate probability in specific point, a specific bar. So it will not, so probability as area under the function in this case will not be considered the function probability. So probability functions generally are built on the axioms of probability theory. If you listen to my second lecture from Lunch and Learn, I talked a lot about the assumptions of probability, not assumption, axioms of probability theory. We talk that for any events, there is always probability that can be 0 or more. The probability of full sample space of all possible random outcomes that we collected will be 1. And if two events are mutually exclusive, the probability of two events will be sum of those probabilities. So basically, when we're talking on mass function or density function, on cumulative function, we're talking about how those functions represent the probability theory and its axioms. So probability mask function, it's really simple. It's the set of all possible probabilities that you can get from the outcomes you collected. Assuming we have a black box with balls from different colors. we have 5 red, 2 and green and blue, and 1 yellow. So for us to pull ball from each color will be specific probability. So red will be 5 from 10, green and blue will be 2 or 10, and yellow will be 1 or 10. So basically this is the random sample space will be our collection of all our probabilities to get at least 1 ball. To give another example of probability mass function and how it can be used, I put together this imaginary example, assuming we're going to the game in Rogers Arena between Canucks and Calgary Flames. And we want to play a game. We say, oh, if we choose randomly 3 fans from the arena, how many of them will be Canucks fans? So because we're choosing 3 fans out of all possible guests that come to Rogers Arena, we only can have restricted number of possibility of choosing Canucks fans. So we can choose 3 people that all fans will be Canucks, and we can 3 people that all fans will be Calgary Flames fans, and all possible combinations of the fans, depending on how we pulling them together. So basically, in this case, number of Canucks fans we wanted to select will be our capital X, and number of numbers that this X can be assigned to small x will be 0, 1, 2, and 3. As this is a home game, we probably will have more Canucks fans in the arena, and my assumption is assuming 20% of fans were Canucks and 20% Flames. So this means that my probability of choosing Canucks fans will be 0.2 and Flames 0.2. Canucks 0.8 and Flames 0.2. So now, from my sample space, from all the possibilities of choosing Canucks fans, I actually can calculate probability. Probability of choosing Canucks, not choosing Canucks fans and only Flames will be 0.2. Probability of choosing Flames fan multiplied by 3. Yeah, because we didn't choose any Canucks fan. And like this, we can calculate very simple probability of 1, 2, and 3 fans. And on the right, I put the table with probabilities. This is basically our probability mass function for each point of X. So I assign specific probability and set of all the probabilities, actually my probability mass function. And another term is cumulative probability function. So people on the Zoom that run their own analysis, like if they run in frequencies, there is frequencies and there are cumulative frequencies. If we're doing it for discrete or categorical variable. So actually it's exactly the same. For any given random variable X, and its probability mass function, probability of X of P of X, we defined cumulative distribution function as probability of choosing X, our X less or equal some kind of point of K. So basically, as I said before, we looking on all possible possibilities of choosing X from our discrete sample space that is less or equal certain number K. Another example, it's kind of very assumptional example. So for example, there is family of 3 children, and if X is number of boys, and in this case, we are assuming for simplicity that the probability of having boy, girl exactly the same, even it's actually not. And we want to calculate cumulative probability of having up to 3 boys in the family. So the probability of having 0 boys will be 0.125. And the probability is calculating again from our sample space that I detonated as S. So we can have family of 3 girls, 3 boys, or any possible combination. So probability of 0 boy will be 0.125. For 1 boy will be 0.375. but probability of having 0 or 1 boy will be actually 0.5. And if we looking for all possible possibilities of choosing the boys, it's from 0 to 3, actually our final cumulative probability will be 0. And if you're running ucode on SAS or R or any other program for cumulative probability, your last line, if there is no missing values, always will be 1. Now, as we talked about probability mass function, I want to talk about several discrete probability distributions. And the simplest distribution is Bernoulli distribution. And I think it's actually based on all discrete probability distribution. It's basically very simple. You doing something only once, and you have probability to succeed, a probability for the failure. For example, if we toss in the coin, there is 50% chance that we're going to get a tail, and 50% chance that we're going to get a head. So below is a graphical representation of this distribution. Yeah, and because we toss in the coin, we're assuming that probability is 50-50. We will have two bars that look exactly the same. So what is Bernoulli distribution in real life? I'm thinking, oh, if I'm doing the test tomorrow, am I going to pass it? And what probability for me to pass this test? If we're looking sport game, we can say, oh, what will be probability for my favorite team to win? Probability of accepting or rejecting any job, probability of rolling 6 dice in one round of the games, or win one round of the lottery. So if something happening with one, there is probability that event will happen, and no, 1 p is probability of success, and 1 minus p is probability of failure. Yeah, why this distribution is very important? Because the next one I'm going to explain new binomial distribution. So actually, if you think about it, binomial distribution, it's basically the base of our logistic regression. Our outcome is 1 and 0, something happened or didn't happen, and we're trying to predict how many events are happening, or what are the risk factors of events happening, and so on. And the basic for it is binomial distribution. It's the most common discrete distribution in statistics. We use it in applied statistics a lot. It's generated from one variable with only 2 possible outcomes. Again, same as Bernoulli distribution, P, it will be probability with success, and Q, or 1 minus P, is probability of failure. So basically, if we perform Bernoulli experiment many times, combinations of all Bernoulli distributions will give us a binomial distribution. Here we're going to a little bit more math, but I will simplify those formulas later. So basically, for any function we working on, either discrete or continuous, there is formula for probability mass function for discrete variable, or develop formula for cumulative function. We can calculate it manually the way we calculated example about Kinect fence, but actually, if we know the formula, we can use the formula to answer our specific questions or specific examples. And if you understand how the binomial distribution works, I think it will be much easier for us and for you to interpret the results where logistic regression based on binomial distribution is used. So basically, probability mass function, it's what I put in the formula on the right. It's NCX, it's basically NCX. It means it's possible combination of choosing X out of n events. Yeah, so it's basically can be written differently using factorial factor. Yeah, so basically, if we have two possibilities. If we want to choose 2 red balls out of 8 balls, we can use formula and look on how many possibilities for us to choose red balls. So basically, it's our sample space. You remember for Kinect fans or for number of boys in the family, I use sample space with all possible combinations. So this formula NSCX actually giving us a simple way by putting the numbers inside the formula, actually know how many possible combinations of doing something we'll have. Now I think if I give you examples where the binomial distribution is used, it's mostly used in a field of drugs as medicine, whatever a new drug is intended to cure a particular disease, or if the drug is effective. And also we can look what the side effects for the drug there are. So basically we can use for all those complicated things like clinical trials, etc. we can actually use binomial distribution. When we try, and like yesterday we talked on staff meeting, we talked about machine learning. By basically binomial distribution or logistic regression can be used to send you spams in the junk spam folder. And also, for example, in the store, when there is a sale in the store, the store actually can calculate how many products will be returned by the customers over the time, and based on this one, they can predict their sales. So I think it's why it's very important distribution, because everywhere you look, you actually can use it. So as everything in mathematics and statistics, the binomial distribution has assumptions. And the assumptions are pretty straightforward and easy. As I said before, we have 2 events, true or false, failure, yes, failure, success, yes or no. When we're doing a binomial distribution, we're looking on a number of independent trials. So basically, to choose something today will not be depending of my decision to choose something yesterday. And for each trial, we're doing the probability of success or failure, it's the same. So we can, it's not like we say, oh, yesterday to choose red ball out of the box was 50% and now it's 70. No, if we're doing the experiment of continuous experiment, doing same thing over and over again, our probability of failure and success always will be the same. So when we're doing a binomial distribution, we only count in number of successes. And this is a summary again on independence of the trials. In every trial independent, which means the outcome for one trial does not affect the outcome of another trial. So trials are independent and outcome from the trials are independent as well. So for example, and here I want to give example of cumulative function again. So assuming we tossing the coin 5 times. And I want to find probabilities that I got 4 times heads. So basically, because I only have 5 independent trials, I only can have probability of 4 heads or probability of 5 heads. And here, using the formula on the right, I actually pull the numbers inside the formula, and I actually calculated my probability of choosing 4 heads will be 532, and 5 heads it will be 1 out of 32. So my total probability of choosing 5 heads will be 3 out of 16. As you remember, based on our axioms of probability, because events are independent, we can sum our probabilities to get the cumulative for total probability. So this is how you can use this binomial distribution basically for any experiment you want to do, assuming that your probability of success is always the same. So here I pull some binomial distributions, and simply speaking, if you do a lot of modification of the formulas I just showed, we can identify in the end that the mean of this distribution is number of independent trials multiplied by probability of success. And our standard deviation of this distribution will be probability mean, probability, or not probability, combination of number of independent trials n multiplied by probability of success and probability of failure, that it's 1 minus p. But what interesting here, if you look, as more independent trials we have, as more our binomial distribution will be looking like normal distribution. Yeah, so for example, on top, I looked something on probability of 0.5, same probability for failure and success, and number of trials was 10, and it's look very symmetric. But if I look on the figure on the right, assuming I still have number of events, number of trials is 10, and my probability is a bit high of 0.8, my graphical representation, my function actually show that it's skewed to the right. But if our probability of success is very small, it will be skewed for the left. But if you look on this, it's if we have enough trials, independent trials, like very big sample of trials, it's actually binomial distribution will become the normal distribution. And this is a base of central limit theorem. It's basically saying that every distribution we have around us, if we have a large enough sample, that the sample can represent the normal distribution. And if you're interested to learn more about this theorem, my next newsletter will describe in more details what it is. Another discrete distribution is Poisson distribution. In my opinion, it's very important distribution as well, because we talk a lot, we go and calculate incidence using Poisson regression. But actually there is reason why we can use Poisson regression or Poisson distribution to calculate the incidence based on the nature of this distribution. Compared to binomial distribution, it's not the possibility of like we have one trial and we choosing failure or success. The Poisson distribution telling us what is the probability of event happening a certain number of times within given interval of time of space. And if you look on the incidence, we are looking how many times the new disease occur or repeated disease occur, recurrence of disease occur within specific time frame, within the year or within the month. It's why Poisson distribution is very suitable distribution for calculating of prevalence or incidence. The Poisson distribution only have one parameter. In statistics, it's called by Greek letter lambda. And for Poisson distribution, lambda, it's actually the mean number of events. So basically below I plotted in Excel the Poisson distribution for different numbers of lambda. And here you can see again that for lambda of 0.5, a yellow line, it's very sharp. But when we're looking for lambda equals 6, we can see that our distribution line that is black, it's very close in reassembling the normal distribution. So why I think to And the standard deviation of Poisson distribution is lambda as well. And here I want to say very important things, because we use in Poisson distribution for a lot of things for like when we're trying to work with the counts or incidents. But the problem is when you want to use Poisson distribution, you need to validate first that your mean and standard deviation are very, very close. Because when you have over dispersed data, for example, where your standard deviation is much larger than mean, you can still use the Poisson distribution, and computer probably going to calculate and give you results, but the results might be biased, because you might, when you're doing anything related to Poisson distribution, you must to ensure that your standard deviation and mean they cannot be in a random sample the same, but they should be like relatively very close. So one of the first application of Poisson distribution was by, I think, Polish statistician, and he tried to investigate accidental deaths by horse kick of soldiers in the Prussian army. And when he was calculating this, actually, he came up with the idea and formulas of the Poisson distribution. And in Poisson distribution, X, like if you can see above the chart, there is formula again of Poisson distribution. In this formula, X is random variable following this distribution. K is number of times the event occurs within a certain period of time. And P of X equal K is the probability that an event will occur K times. E is a mathematical number that it's 2.7 usually, and both variance and mean of this distribution will be lambda. So what assumption of Poisson distribution? If as anything in statistic, the events are independent. The rate of the events through this time is constant. So the rate of how events happening within the time cannot decrease or increase. Events can occur simultaneously, so you can have one event per point of time, and mean and variance are equal. So for example, when we can use Poisson distribution call centers, when they need to know how many calls expected per hour in the center, so they will have enough staff to answer the question. Or like restaurants, they need to know how many staff to bring to the restaurant. So generally, based on historical data, you can predict how many people or customers will be in the restaurant on a specific day, and you know how many people to bring for work. Or for medicine, it will be relevant, for example, during the summer, during the winter where it's very snowy and icy, what will be rate of arrival of trauma patient to our ED. I give you a little bit more example, and I try to make the example kind of related to health. I don't know if it's like there is a lot of reason in it, but basically we know that 15% of women on average have miscarriage, and we want to find the probability that in the sample of 20 women that visit in our clinic today, less than 2 women will have pregnancy resulted in miscarriage. So basically we work for half day. We usually see in our office 20 women. We know probability, generally average probability of miscarriage is 15%, and we want to estimate how many women with miscarriage will be in our office of each day. So again, I'm using the formula of Poisson distribution, and it's really handy, simple formula. And again, the formula we use in factor, so number of possible events, number of possible combination of event. So in this specific sample, for this formula, our n will be 20 women. Our lambda will be 3 because it's kind of logically is number of women multiplied by probability, because lambda it's kind of mean average of events. And we can calculate what is probability of having less than 2 women in our office with miscarriage. So basically using the cumulative probability formula, the cumulative probability of sum of all related probabilities, we need to sum probabilities that we will not see any woman with miscarriage today in our office, or we will have see at least one woman. Because it's easy 0 or 1. And if you fit all the numbers in this formula and calculate it using calculator, we will know what will be the probability of woman to be in we'll know the probability of having less than 2 women in the office with miscarriage. And here what I did, I used this formula and I calculated probabilities for having 0 women with miscarriage to 10 women's miscarriage, and you can see the probability is increasing slightly and after the decreasing, and this is because we said that in average probability of women having a miscarriage in average is 15%. So you can see that it's going a little bit up and down, but the center distribution will be between 2 and 4 miscarriages. So now you can see that we saw that Poisson distribution and binomial distributions look kind of the same, and for large enough samples reassemble the normal distribution. So there are some similarities and some differences for those two main discrete distributions. Both distributions can be used to model the number of occurrences of some event. In both distributions, there is an assumption so our events are independent. But what the difference between those two? In binomial distributions, there is fixed number of trials. We say, oh, we're going to flip our coin 3 times, what probability of head? In Poisson distribution, we don't have number of independent trials, but we're looking for there can be any number of events occurring during certain period of time. Yeah, so we're not looking for independent trial with success or failure. We're looking on how many events over a period of time we will see, and this will be represented by lambda. In Poisson distribution, actually, it's a limiting case of binomial distribution which arise when the number of trials n increases indefinitely and our lambda is np. So you remember when I showed that example in previous slide about the miscarriages, I said I'm going to calculate lambda as n multiplied by p. And this is actually because Poisson distribution is actually a limited case of binomial distribution, and we can do this assumption to link both of those distributions. So now we're going to look of continuous density functions, or basically we can use them as continuous distributions. So what is a reminder that continuous random variable differs from discrete random variables that takes on an uncountable and infinite number of possible outcomes between 2 points. So basically finding for probability of something for continuous function, it's probability of x when x is between 2 points A and B. And examples of continuous distribution can be exponential, gamma, normal, and chi-square. I'm going to talk about exponential and normal distribution, and I touch a bit about chi-square distribution because chi-square we use a lot in our analysis. So basically, what is exponential distribution? It's actually related to Poisson distribution, but it's measuring time between 2 events in Poisson point process. So Poisson point process in this case will be number of events of the time. We're running the Poisson process and calculating number of events over time, but time between events. It's not necessarily the same time, and time can be measured by exponential distribution. For example, And of course, I put the formula of exponential distributions that I'm not going to get into it. In this case, we have example. For example, what is the probability of receptionist to spend 5 minutes with a random patient? Yeah, because we need to know how many receptionists we want in our office, and we need to know what is probability spending specific number of minutes or hours with specific patient. So if you're using probability density function formula, we can calculate that the probability of receptionist to spend 5 minutes with any random patient will be 0.072. But I can say, oh, I don't know, maybe I want to calculate probability of receptionist spending time with the patient 4 or 5 minutes, can be either, or like 3 or 5 minutes. So this way, we're not going to use probability density function. We're going to use cumulative function because we want combination of two different probabilities. And again, in this case, I need to calculate probability to be between x being between 4 and 5, and if I fit all the numbers in cumulative distribution function, I'm going to calculate probability of less than 5 events, probability of less than 4 events, and here as the difference between two probabilities will be my answer to the question, what is probability of spending between 4 and 5 minutes for each patient. It's kind of a bit stupid question here, like I come up with it from my head, but it can be applicable for more real situation when you want to measure something. So it's just a small example to show how I did small example of exponential distribution to show how exponential continuous distribution is extension of Poisson distribution. But now we're going to go through the main distribution of statistics that we will not be able to do any test or any analysis without it. It's a normal distribution. Normal distributions are important. It's not one, it's a group of distributions. So normal distributions are important in statistics and are often used in science to represent real valued random variables whose distributions are known. So, you know, when we're doing analysis, we like linear regression. Our assumption is that our continuous variables we use distribute normally. It may be not necessarily true, but we assume that the distributions will be normal. Normal distribution is also known as Gaussian distribution. And we can say that its probability, it's the distribution that's symmetric about the mean. So usually we have mean in the center, and we have the bell curve, and it's symmetric around the mean. There is normal distributions that are symmetrical, but there are normal distributions that will not look symmetrical. So many naturally occurring phenomena in our lives that will be approximately normal distribution. And the normal distribution actually again made relevant by central limit theorems that I already mentioned when I discussed binomial distribution, which states that the average obtained from independent and identically distributed random variables always will be normal. So it's not number of events for larger samples that will be normal. If we take in independent identical random variable and basically we're resampling multiple times, the average of our resampling will be resampling normal distribution. Shape and properties of normal distribution. It's the normal distribution, the classical normal distribution, it's symmetric, where mean, median, and mode are equal. And there is a empirical rule for classical normal distribution. around 68% are within one standard deviation. So it's first two orange line from the mean, right and left. 95% will be within two standard deviation from mean, and 99.7% will be three standard deviation of mean. Why it's important? Because we always using confident intervals of 95%, and it's actually for normal distribution, its values within the two standard deviation from the mean. There's additional important parameters for normal distribution is skewness and kurtosis. I'm not going to go in details what it is, but actually it's showing how right to left our normal distribution is skewed for the classical distribution. So you remember in statistics course they say left-tailed or right-tailed. This is measured by skewness and kurtosis. And on the left I put historical notes on how this distribution was developed, but I'm not going to go into it right now. So as I said, normal distribution, it's not one, it's a set of different distributions. And I try to represent graphically two examples. On the left, we have normal distribution with different means. So basically, in this case, the shape of distribution is not going to change, but it's going to move on our axis to the right. And the example is about SAT scores. And I took it from the internet, of course. But if we leaving the mean the same and changing the standard deviation and standard deviation go up, our normal distribution will be more peaky and will be more skewed out around our mean. So below it's the formula of normal distribution that every statistician should know by heart. And basically I explain in here what are the values in this formula. Mean is mean, S is standard deviation, sigma is standard deviation, sigma square is variance, X is value of variable, and f of X is actually our probability density function. Standard normal distribution, also called Z distribution. It's a special normal distribution with mean of 0 and standard deviation 1. So basically, every time we're doing something using normal distribution, in order for us to calculate significance of p-value, we use a standard normal distribution with the mean 0 and standard deviation of 1. And it's very easy to convert any normal distribution to standard normal distribution. And why we convert normal distribution to standard? To find the probability of the observation is distribution falling above or below given value. We can find probability that the sample mean significantly differ from a known population mean, and to compare scores of different distributions with different means and different standard deviation. So this is examples of normal distribution. Like for example, on the right, we're looking on population height, and it will be normal distribution. Or if we using the rolling of the dice a lot of time, we will have in the end the normal distribution, and there are some probabilities of having different combinations of rollings. So how standard normal distribution is used? I give a simple example. I actually took the data from the SAT score of specific year. In this year, the when it's in 2015, when MCAT was done, they calculated the mean of score of 500, not sure what it is. And you can see that the maximum score was 528 and minimum score for MCAT this year it's 472. So I want to know, I want to go to medical school, and I want to think, oh, in general, taking in consideration, I have this data from 2015. I want to estimate my probability to get a MCAT score of more or equal 510. So first, what we need to do, we need to standardize this distribution to Z distribution. And simple formula of calculating Z, and Z is the most important letter in statistic, yeah, Z distribution Z, because based on this one, we can calculate everything. So in order to get this the Z, it basically our X and our actual normal distribution minus mean divided by standard deviation. So for this specific example, my X is 510 because I want my score to be more than or equal 510. My mean will be 500 and my standard deviation is 4, and I took it from the actual data of MCAT from 2015. So I calculated my Z based on this formula, and my Z is 2.5. What it means that equal 2.5, it means that the score of 510 is 2.5 standard deviation away from the mean, because remember that normal distribution is have a standard deviation of 1. Yeah, so it's 2.5 multiplied by 1. Next, we can find the probability of the score using this table. So for this value of Z of 2.5, if you're looking for probability in the table or on the calculator or Googling it, we will know that probability associated with the Z number will be 0.9938%. And I guess based on this one, I can realize that there is no chance I'm going to get 510 on MCAT. So this is just basic example how you can take any normal. This was a basic example of how you can take normal distribution, standardize it and calculate and use it on any example or any analysis you wanted to do. So now I spent 2 minutes about chi-square distribution. We're using chi-square a lot, but actually what is chi-square? Chi-square, it's not an actual distribution. What I mean, it cannot be used in real life. It's completely statistical or mathematical. So basically what it says, it's continuous distribution that we widely use in hypothesis testing. And the shape of chi-square distribution is determined by parameter k, which represents degree of freedom. And in my next lecture, I'm going to talk a lot about degree of freedom. Very few real world observation from chi-square distribution we can see in real life. And basically the main purpose of chi-square distribution is using it for hypothesis testing, but and not describing real world examples. So in here, I put an example of a chi-square distribution for different number of k. So basically, I'm not going to do an examples details of this one, but I just wanted, you can read it later, but I just wanted to say that chi-square distribution, it's completely mathematical statistical distribution, but understanding it very important when we testing the hypothesis. So more generally, if you sample from k-independent standard, you have basically a sample of a k-independent standard normal distribution, and you using square sum of the values, and you get in your chi-square distribution from degree freedom of k. Thank you. Do you have any questions? I know it was a lot of information. Any questions?
No, ma'am.
Good.
Yeah, this is my first class. So where can I like see the previous classes recordings? And
Yeah,
is
the two lunch and learn videos are available of our website. So if you go in Google VHRI Lunch and Learn, you will have all the lectures that we currently put there that already recorded, and you can listen to 2 of my lectures, or you can listen to other lectures we presented during the Lunch and Learn.
Sure, thank you. And is this like a regular everyday session?
No, my sessions will be every last Thursday of each month. Yeah, so for now I developed curriculum for 3 different lectures. So this one was distribution, and next one actually will be why p-value is not important. And after that we'll go for additional lectures. And for 2024, I have in my head what I want to talk, but I didn't develop it in more details yet. Yes, but I'm planning to do it if everything is fine. I'm planning to do my lectures once a month, basically, and you will get notification if you get a new e-blast or newsletters from VHRI. But also if you Google Sabina Stat series, you will see information about my series on the website.
Got it. Yeah. Thank you so much.
Thanks. Okay, thank you.